So, Bismillahirrahmanirrahim. So, this is the sixth lecture, and today we will start from article number 2.3. That one is the applications of Schrodinger's wave equations. Okay. So, in this, so we know that using the Schrodinger's wave equations, we can solve various problems related to potential functions. So, let's start from article number 2.3.1. That one is electron in free space. So electron in free space, that means there is free space means there is no potential functions. Okay. So if we start with as a first example, we are applying Schrodinger's wave equation considering the motion of an electron in free space. So we are considering that the motion of an electron in free space. So if there is no force acting on that particle, that means no external force is there, then the potential function v of x, if there is no external force, then the potential function v of x should be constant. Okay. Now we assume that the potential function v of x equals to 0 for all values of x. Then the time dependent wave equation should be, so we know that the time independent wave equation should be from, if we go to article number 2.313, that one was Schrodinger's wave equation. Okay. So that one is second order derivatives of phi of x plus 2m divided by h bar, or h naught square e minus v naught x psi of x. Now if we assume there is no external force or no other external potential, that means v of x, this v of x should be equals to 0. Okay. So if v of x equals to 0, then our equation should look like this. Is that okay? Now we know that, so this one is a second order differential equation. So we know that second order differential equation means d square y divided by dx square plus x m or x a should be equals to 0. Isn't it? The second order equation looks like this, where y is the psi of x and m equals to 2 m e h naught square, and psi of, sorry, this should be not x, this should be y of m. Okay. So we know that this solution is the generalized form of this solution, solution of this differential equation is psi of x. Psi of x should be a exponential, that means e to the power j mx or jm plus b e to the power minus j mx, or if we consider with these equations. Okay. Now there are two unknowns. So look, this parameter is known, this parameter is known. There are only two unknowns, right? So we know that in case of boundary conditions, we have two boundary conditions. So we can also find out this value of a and b using those two boundary conditions. Now if we recall the time dependent portions of these solutions, so time dependent portion means psi of t equals to e to the power minus j e divided by, so we have derived these equations previously, isn't it? Now the total solutions should be psi of psi x of t. That means whenever we are considering that potential function psi with both with respect to, that means we are considering for both space independent and also for time independent, then our equation should looks like this, because we know that e to the power x plus or multiplied with e to the power y, that means e to the power, this should be equals to e to the power x plus y, isn't it? So if we multiply the time dependent solutions with the time independent solutions, then the total solution should look like this. Only this exponential term will be multiplied with the previous solutions. So similarly, we have two unknown parameters. That one is a and that one is b. Now this wave function solution is a traveling wave. this wave function solution is a traveling wave. Why this one is known as traveling wave? Because this, for the plus sign, it will move in the x plus directions, and for the y sign, it will move in the minus x directions. So look, here they have also explained these things. The first term with the coefficient a, the first term with the coefficient a is the wave functions traveling to the plus x directions. Whereas the second term, that means the coefficient with b, is a traveling with, that should be minus x direction, isn't it? So these, so the values of these two coefficients will be determined with the boundary condition. I have told these things previously. Now assume the moment, assume we have a particle having in the x direction. So that means we are considering that our wave is moving only these directions. So if the traveling wave for x direction is for a constant, and for this negative minus x direction is b constant. So if we, for simplicity, if we consider that this traveling wave is only moving in plus x directions, then we have to, so if that one is only plus x directions, that means the value of b should be equals to 0, isn't it? So the coefficient of b should be equals to 0. So we can write down this, so we can write down this thing. If b equals to 0, that means we can neglect this part, so only this part will be there, right? So that should be a e to the power, that means a exponential j k x minus omega t. So look, so we are considering this term multiplied with this term as constant k. So where k is the wave number, that should be equals to 2 pi divided by lambda. Is that okay? So if we compare these things, that means a time independent or time dependent traveling wave solutions, then we can write this lambda. If we compare these things with our uh, main equations, that means with these equations, then we can write down lambda should be equals to h divided by root over 2 me. Again, from de Broglie's wave particles duality principle, we know that lambda should be equals to h divided by p, where p is the momentum. Okay. So for a free particle, a well-defined energy will also be an well-defined wavelength and the momentum. Now the probability density functions. The probability density functions, psi of x of t and asterisk sign of psi of x of t, that should be equals to a with another asterisk sign of a. That means these two are complex conjugate, isn't it? So if that these two are complex conjugate, then the this should be equals to, a square. So the a free space particle in a well-defined momentum can be found anywhere with equal probability. That means look, this a multiplied with a conjugate, this one is a constant term, that one is a square. So it defines that a free particle with an well-defined momentum, that means if we consider a particle with an well-defined momentum, then it has equal probability in every places. So this result is the agreement with the Heisenberg uncertainty principle. That means if we can determine the momentum, then this this is impossible to determine the position of a particle, that means the exact position of that particle. So we are defining this psi of x, so psi of x is nothing but the probability functions of finding an electron. Look, so please do not forget that what is, so this is a fundamental question, what is psi of x of t? So psi x of t, look, psi x of t is the probability functions. That means this one is the probability for finding that electron, both in time and both in space. So this doesn't mean the exact positions or exact time. So these determine the probability functions. That means probability of finding that electron. So we have so we determined that the probability for a free electron. Look, so for a free particle with an well defined momentum means if this p value is a constant value, that can well defined momentum can be found anywhere with equal probability. Why this one is known as equal probability? Because from these two, psi x of t with asterisk sign of psi x of t, that means asterisk sign means this conjugate equals to a with a conjugate, that means that one is a square, so that one is a constant. Okay, now go to article number 2.3.2. That means look, this one is an infinite potential oil. That means we will have three regions. The first regions will be the infinite potentials, then after that region 2 will be the zero potential, and the again third region is a zero potential. Look, the problem of a particle in an infinite potential oil is a classical example of bound particle. So the potential V of x as a function of the position of this problem is shown like this. So at x equals to 0, this potential was infinite. After that, from x0 to xa, this potential equals to 0. And again, at position a, that means x equals to a, this potential is again infinite. Okay. Now, so we know that the time independent Schrödinger's wave equations looks like this. So we have found this things in article in equation number 2.13. So whenever is finite, so if we consider this e is a finite function, then psi of x should be equals to 0 for both the region 1 and 3. So a particle cannot penetrate this infinite potential barrier. So the probability of finding particles in region 1 and in region 3 is 0. So if this E value is a finite value, if this value is a finite value, so the wave that means the wave functions must be equals to 0. Okay. Now for the second reason, so that means if we divide these things within three regions, that means region 1, region 3, and also region 2. So for this region 1 and for this region 3, these two should be, the result of these two should be same. That means the psi of x should be equals to 0 for these two particular. Now we have to determine for only this region 2. Now for the time independent Schrödinger's wave equations for region 2, that means where v of x value equals to 0. Because in this region, so we know that v equals to 0 here. So our equation should looks like this. Now for a particular solutions, these solutions should looks like. So I think you know about from your first semester, you know the solutions of the second order differential equations for a particular. So if the right side portion is equals to 0, so these solutions can be determined in the form of a1 cos k of x plus a2 sine k of x. So similarly, where k is equals to root over 2me divided by h naught square. Now, using the first boundary conditions, that is the wave function psi of x must be continuous. That means psi of x of 0 and psi of x of a should be equals to 0. Applying these two boundary conditions, if we apply x equals to 0 in this equations, psi of x equals to 0, then cos of x, that means a1 should be equals to 0 and this portion equals to 0. So we can define that a1 should be equals to 0. A1 should be equals to 0. Now we have find out a1. Now what left here? So we need to find out the value of a2. Now for x equals to a, we have a2 sine k of a. This should be equals to 0. So from here we can find out the value of k. So k of a equals to n pi. So k should be equals to n pi divided by a. Now again there will be two different solutions. Now the coefficient a2 can also be found for the normalized boundary conditions. That one is given in the equation. So equation 2.18 is the another boundary conditions. That one is psi of x with the conjugate of psi of x, and if we integrate from minus infinite to infinite, this should be equals to 1. So if these things equals to 1, then the real function psi of x should be equals to the conjugate function psi of x. So this defines that these two are same. So if the function is a real function, then there will be no conjugate part. That means there will be no minus j part. So if we integrate from 0 to a, from 0 to a, because we need to only determine the potential only for this region, right? For the region 2, that one is x value equals to 0 to x value equals to a. So if we integrate from 0 to a, then we know that how to integrate. So I think all of you know about these integrations from 0 to a. That means we need to also divide. So how to determine this thing? Okay, so a2 is a constant, so we will keep these things outside. So I think you know how to integrate sine square x dx. I think all of you know how to integrate this thing. How to integrate 2 sine square x dx divided by 2, right? So 2 sine square x, what is the formula? 1 minus, so yeah, there will be an integrated sign here. So 1 minus cos twice x, right? Integrate, and that should be divided by 2. I think you know, and from that integration you can easily find out the value of a2. So the finally the time independent solution psi of x, the time independent solution psi of x should be root over 2 by a sine n pi x divided by a. Now look, this solution represents the electron in the infinite potential wave, and that one is an standing wave solutions. Not that one is not a traveling wave solutions. So traveling wave solutions means that one is both time independent. That one is that one will move for both the directions with respect to time. Now the parameter k of these solutions is defined as equation number 2.29 and 2.32. 2.29 k equals to this, and here k equals to n pi. So twice me divided by h naught square equals to n square pi square a square. So E should be equals to h bar square n square pi square divided by 2 ma square. So this n means the shell number. Now the potential was, so for the particle in the infinite potential oil is an wave function, and that one is given by psi of x equals to root over 2 by a sine k of x. So this implies that the total energy of the particle can only have discrete values, and this result means the energy of this particle is a quantized. The energy of the particle can only have the particular discrete values, because so this x for a particular x, or the particular values of x, this will have a particular value. So this one is a quantized value. So using these formulas, you have to solve the example number 2.3. Very straightforward. So you know this h naught, so h bar so equals to h divided by 2 pi, where h is the Planck's constant. So you know the value of pi equals 3.1416. Then m equals to mass of this electron, and a equals to, where a is the wavelength. So this wavelength or the width is given as 5 angstrom. So using that formula, we can find out the E1 value, E2 value, and E3 value. So look, so these things, these values or the unit of this energy is given in the electron volt. So how to convert this electron from joule to electron volt? If we divide by 1.6 into 10 to the power minus 19, so that one will be in electron volt. Now, the energy functions, these energy functions can be defined in this way: from before 0, that one is constant, and after 0, so from x equals to 0 to a, that one is quantized, and after from 0 to a, this energy value, so this one is psi n value. So psi square n means that one is the square of sine square, and that one is the value of the sine wave, that means the square of the sine wave, and try to solve the test problems. Now, if we move to article number 2.3.3, that one is the step potential. So step potentials means that one will have only a step potential, step function. So if we consider that that one is an step potential, so this one will have in the plus x directions, and up to the from minus infinity to 0, this value should be equals to 0. Now for the barrier height, we are considering that E should be less than V naught. Now we know that from equation number 2.13, this one is very important. That one is the time independent Schrodinger equations, solution of the time independent solution equation. So this one is like this. So if we consider that v of x, this v of x equals to 0. So v of x equals to 0. That means before before the positions x equals to 0. That means here we have two reasons, reason 1 and reason 2. So we are calculating only for first for this reason. So the solution will be something like that: a1 e to the power minus e to the power j k1x, and b1 e to the power minus j k k1x, like this, where k1 is the constant and it should be equals to this. So we have solved these things for the first problems. That means that one is in article number 2.3.1. So before the positions, that means the before the these positions, that means at x equals to 0, we can determine the value of a1 and a2 using the boundary conditions. Now we will go for the reason 2. That means we will have v equals to v naught. V equals to v naught means we will have a constant value. That means this isn't it a step functions, right? So in that case, so we'll have the value of v naught there, and look, this v naught is also a constant. So we can assume these two terms as a constant terms. So again, the solution should looks like this, isn't it? For x is greater than or equals to 0, then we can determine the k2 values. So now if we use the boundary conditions, that means within this limit, the b2, that means before this we'll have a1, and before this we will have, sorry, a2, and after that we have b2. And if we put that from minus infinity to 0, this value equals to 0, the first boundary conditions, then it will define that b2 value equals to 0. So psi 2 of x equals to a2 e to the power minus k2 of x. Now the wave functions, if that one is a continuous, that at x equals to 0, so psi of 0 should be equals, psi 1 of 0 should be equals to psi 2 of 0. So that so the formula will be, a1 plus b1 should be equals to a2. Now if we put these two values in their generalized solutions, then we will have jk1a1 minus jk1b1 should be equals to k2j2. Now from these two equations, that means from this equation number 2.47 and 2.49, we can find out the values of b1 and a2 in terms of a1. So from this two equation we can find out this b1 value and a2 value. Very simple things. Now we know, so B1, this one, the reflected probability density function, that means that this conjugate part. So B1 and the multiplication of B1 and B2 conjugate, that means B1, sorry, B1 conjugate means this J value should be minus and the rest of the value should be same. So then our equation should looks like this. I am not deriving the mathematical part. So if you face any problem for deriving this mathematical part, we can discuss these things in the problem solving class. And this one is known as the reflected flux to the incident flux. The reflected flux to the incident flux, that one is vr b1 b2. So these upper portions is the reflected flux, and the denominator is the incident flux, that one is vi a1 and a1 conjugate. So we know that T max equals to T equals to the kinetic energy T equals to half mv square. So using that formula, so we can for the maximum values of E at V equals to 0, or at V equals to 0, this E value should be equals to T. So using that formula, we can find out K1 should be equals to half M divided by H bar. Same way, we can find out if this one is VI, the formula should be like this. If that one is VR reflected one, then that formula should be like this. So this, if we reflected and the incident, these two are equal, then these two will cancel each other. So the reflection coefficient will be like this. If we put the value of real part and conjugate part, then our we will see that the summation or these two numerator and denominator, these two will cancel each other, and the reflection coefficient value should be equals to 1. So this reflected value r equals to 1 implies that the particle incidence on this potential barrier for E is less than E less than V naught is reflected. That means the particles are not absorbed or transmitted. So if reflected value equals to 1, that means this particle is not. So if we consider this, so full part is reflected. Nothing is transmitted or nothing is absorbed in this surface. So this result is entirely consistent with the classical physics things. Okay. So look, this part is important. This result implies that there is a finite probability that the incident particle will penetrate the potential barrier. The incident particle will penetrate the potential barrier and exist in the region 2. This probability of the particle penetrating and the potential barrier is another difference between the classical and the quantum mechanics. Okay, so in the quantum mechanics, this penetration is clearly not allowed. So using this formula, try to solve example 2.4 and try to solve the practice problem 2.7. Now, if I move to article number 2.3.4, that means the potential barrier. So potential barrier means I will have a step functions. Look, the first condition was like this. Previously, we have a functions. After that, 0. Then after that, function like this. Now, in this reason, we will have again three reasons: reason 1, reason 2, and the reason 3. So for the reason 1, we will have 0 values. For the reason 3, we will have 0 values. And for the reason 2, we will have the V naught values. So that one is known as potential barrier. So same way, we can find out the solutions for this. If we consider that for this reason is psi 1, this one is psi 2, and this one is psi 3, then using the same formula we can write down the solution like this. So this problem or this article is nothing but the accumulation of the previous problems. Then we will find that this one is the K1 constant because we have derived these things previously. This one is the K2 constant. So again, similarly, if we try to find out the transmission coefficient T, that one is A3 with the conjugate A3 and A1 with the conjugate A1. And we can conclude these things. We can conclude these things. This T should be equals to 16 E by V naught 1 minus E by V naught in this way. So try to go through these things and solve the example number 2.5 and also this test problems. So this will be the end of our sixth lecture, and in the seventh lectures we will start from article number 2.4 inshallah. So if we face any problem, so we can about understanding or about the numerical problems, so we will discuss these things in the problem solving class. So after this, in the before the seventh lecture, I am concluding the sixth lecture here. Thank you.